Modern high-frequency trading operates in an adversarial ecosystem where execution relies on nanosecond precision and millions of discrete systems are deeply coupled. Despite this tight integration, standard financial infrastructure treats its vital signs, market data feeds, network latency, compute load, and capital risk limits as completely separate data streams tracked on isolated, scalar dashboards. When a market anomaly hits, these isolated monitors fall out of sync. A delay in market data might trigger a network throttle, which misaligns with the compute queue, causing automated safety controls to collapse under contradictory inputs. A trading strategy optimized purely for market price signals is effectively blind to its environment. It will execute itself into massive losses if it ignores sudden spikes in network jitter or unexpected counterparty credit limits. Relying on isolated infrastructure metrics is structurally unsafe. Real-world financial failures do not happen in just one domain. They are cross-modal and highly coupled. To fix this, engineers must map the entire environment. The financial services mode map includes market microstructure, execution gateways, compute health, risk capital, and even the system's current cybersecurity posture. But attempting to calculate the joint probability distribution across all these states simultaneously triggers a combinatorial explosion. The mathematical volume of this state table makes real-time forecasting impossible using standard methods. The system would freeze just trying to read its status. A 2026 postdoctoral white paper details a structural solution to this dimensionality curse, transitioning financial infrastructure to a tensor-geometric paradigm, utilizing the Predictive Tensor Control Plane, or PTCP, and Tensor-Network Quantum Gravity, or TNQG. To safely navigate high-dimensional market stress, financial automation requires a unified, compressed mathematical object that can hold all of these operational variables at once. The Predictive Tensor Control Plane initiates this process. By compressing massive arrays of multimodal telemetry into a single tractable state object, it achieves this through Tensor Train decomposition. This mathematical operation factors the massive, unmanageable Pontodable table into a sequential product of low-rank cores. By replacing the full grid with these interconnected cores, storage requirements drop from an exponential scale down to a polynomial one. This reduction in computational weight is what makes real-time, high-frequency updates feasible. This compressed probability tensor now functions as the single objective source of truth. Both quantitative research simulations and live production execution systems read from the exact same mathematical state. Compressing the state across all modes is the essential mathematical operation that allows the system to accurately forecast cross-domain interactions. There is a common misconception that network routing and high-frequency trading is simply about finding the absolute shortest physical length, a fiber optic or microwave cable between two servers. This is where Tensor-Network Quantum Gravity, or TNQG, enters the framework. Here, TNQG is not deployed as a physical proof of quantum mechanics, but strictly as an operational translation dictionary. TNQG maps the tensor's operational limits and network capacities into an effective latent geometry of the market. In this operational geometry, physical distance is secondary. A network path might boast exceptional average latency, but if it suffers from high jitter, stale data feeds, or maxed out credit limits, the mathematical length of that edge dynamically stretches, rendering it longer to the system. This is a block diagram showing the unified reference architecture. By placing the PTCP tensor control plane upstream of the raw exchange infrastructure, telemetry flows directly into the control plane to inform the current geometry. Within that control plane, the system calculates a conditional value at risk, or CVAR, objective. It evaluates the expected cost and potential tail risk of a given action, and then proposes an optimal execution route or system throttle. However, this mathematical prediction is not granted direct control. The proposed action must first pass through the safe actuation layer, which acts as the system's ultimate gatekeeper. This separation introduces bounded actuation. It enforces the strict principle that algorithmic forecasts, no matter how confident, never possess unconstrained authority over live trading capital or actual market execution. The safe actuation layer projects every proposed move against a hard set of invariants. It enforces pre-trade credit limits, order size collars, venue eligibility rules, and automated kill switch conditions before any signal reaches the market. High-speed mathematical forecasting is only commercially and legally viable when it is strictly bound by these hard regulatory and operational risk invariants. This infrastructure also addresses one of the most notorious failures in quantitative research: trading strategies that show massive profits in a historical backtest, but immediately bleed capital when deployed into live production. Conventional simulations fail because they replay pristine historical price data in a vacuum. They completely omit the critical feedback loops of infrastructure latency, order book queue saturation, and exchange throttles. The PTCP and TNQG architecture enables a true financial digital twin. Using the same tensor modes in research and production, researchers simulate precise physical constraints. Within this twin, they deform the operational geometry, stress testing algorithms by introducing feed degradation, limit breaches, or cyber anomalies. Evaluating an algorithm's execution against this integrated operational geometry is the only accurate way to close the costly gap between simulated research and live production. Beyond performance, any automated algorithmic trading model must meet strict regulatory governance requirements. It must be comprehensively auditable, and its operating assumptions must be mathematically falsifiable. TNQG provides accountability through the residual test, a mathematical diagnostic measuring the mismatch between the reconstructed geometry and observed market behavior. A spiking residual proves the operational market regime has departed from the stable geometry the model was trained on, triggering a halt. It is critical to state that PTCP and TNQG do not generate trading alpha on their own. Furthermore, no geometric framework can ever replace the need for strict market access controls, rigorous model validation, and human accountability. What tensor-geometric automation does is transform fragmented, fragile financial pipelines into a single coherent system. It builds an architecture where market stress is predictable, operational risk is safely constrained, and algorithmic behavior